Welcome back. In this video, we are going to solve exercises 6 to 9 of chapter 4. Exercise 6 is very easy, very similar to exercise 5. We have a self-map from 0, 1 to itself, which is continuous. We have to show that f has a fixed point, not necessarily unique. Graphically, in this case, this means that the graph of f, if you draw it, intersects the first bisector at some point x. So this is easy because we can introduce the auxiliary function g of x equal f of x minus x. Now, it's very important to pay attention to the fact that f maps 0, 1 into 0, 1 because g of 0, now in this case, is just f of 0. But f of 0 is between 0 and 1. So it's bigger or equal than 0, first thing. And second thing, g of 1 is f of 1 minus 1. But f of 1 is also in the interval 0, 1, so it's less or equal than 1. Therefore, g of 1 is less or equal than 0. Okay, so 0 therefore 0 is between g of 0 and g of 1. So by the intermediate value theorem, g vanishes at some point, and the point where g vanishes is a fixed point of f. Okay. So this concludes exercise 6. Exercise 7, open-ended questions. Is the product of path-connected spaces path-connected? Okay, because we proved in the course that the product of two connected spaces is connected. So what about path-connectedness? First question. Second question, if A is path-connected, does it follow that A bar is path-connected? Because we know that if A is connected, then its closure is connected as well. Third question. A union of path-connected spaces having a common point. Is the union path-connected? Okay, we know that this is true for if you replace path-connectedness by connectedness. And last question, what about the continuous image of a path-connected space? Okay, so the answer to the first question is yes. And the proof is actually easier than the proof of that the product of two connected spaces is connected. Because if we have two path-connected spaces x and y, and we consider two arbitrary points AB and CD in xy. So A is in x, C is in x. So since x is path-connected, then we can join A to C by a path that I call f. Okay, so f of 0 equal A, f of 1 equals C. F is just continuous. And since y is path-connected, we can join B to D by a path G. And now if we consider the path whose components are fg, so it's continuous, then at 0, the value of fg at 0 is AB, and the value of fg as 1 is CD. So therefore, we can join AB to CD by a path in the product space x times y. Okay. Second question. You should have, to answer such questions, actually, you should have a clear repertoire of examples and counterexamples. Okay, so we know that if A is connected, then A bar is connected. But we gave an example of a connected space which is not path connected, and this was the topology sine curve that we called S bar. Okay, so S, which is the graph of a continuous function, is path connected. Okay, but its closure S bar, the topology sine curve, is not path connected. Okay, so the answer is no. Third question. Yes, the answer is yes. Take a common point P in the intersection of all A lambda and consider 2 points A, B in the union. Then A belongs to some A lambda 1 and B belongs to some A lambda 2. Now P belongs to both A lambda 1 and A lambda 2 because it's in the intersection. Since A lambda 1 is path connected, we can join A to P by a path in A lambda 1, so by a path in X, and therefore a path in the union. And since A lambda 2 is path connected, you can join P to B by a path in A lambda 2, and therefore a path in the union. Therefore, by composing or juxtaposing these two paths, you get a path from A to B in the union. Okay, and therefore the union is path connected. Last question, yes. let X be path connected and let F be a continuous map from X to another space Y, we have to prove that f of X is path connected. So we take 2 points in f of X. So these 2 points are necessarily of the form f of A and f of B, where A and B are in X. Okay, now, since X is path connected, we can join A to B by a path phi. Okay, I have to use another notation than f because f was taken. So if phi joins A to B, then f of phi joins f of A to f of B, because if phi of 0 equal A, then f of phi of 0 equal f of A. And if phi of 1 equal B, then f of phi of 1 equal f of B. So, and of course, the composition of two continuous maps is continuous. So f of phi is now a function from 0, 1 to y, which joins f of A to f of B. Okay, it's a path in f of X, actually. So, yeah, therefore, this concludes exercise 7. Exercise 8, also an open-ended question. We know that if A is connected, then the closure of A is connected. But what about the interior and the boundary? Okay, here we need some imagination, actually. So the answer to both questions is no. And this is one example. If you consider two closed disks in the plane, okay, that are connected by a line segment joining them, you can draw a figure. Then the interior of this set actually is just a disjoint union of two open disks, so it's disconnected. You can also take simply two tangent closed disks. When you remove the boundary, so you get the interior, you get two open disks that are disjoint. Okay, and so the interior is not connected in this case as well. So please draw a figure to see what's happening. And by the way, sometimes I accept in the exam a proof by figure, because when you draw a figure, I understand that you understood. I understand that you understood what we are talking about. Okay, because sometimes writing equations may be cumbersome. So a proof in topology, a picture in topology may be accepted sometimes as a proof. Okay. Now, what about the boundary? Of course, no, because you can take an interval, a non-trivial interval, AB, with A strict less than B and R. Then this is connected, but the boundary is just the 2-point set AB. The 2-point set AB is not connected, okay, because it has a separation. Okay, so, and of course, you can invent other counterexamples. Okay, so this concludes exercise 8, and now the last exercise in 3 parts. If A is a subset of a topological space, we say that A is nowhere dense if the interior of the closure is empty. And as you know by now, we say that A is totally disconnected if the only non-empty connected subsets of A are the singletons or one-point sets. Okay, first question, give an example of a nowhere dense set and an example of a totally disconnected set. You should be able to do that. Second question, give an example of a totally disconnected set which is not nowhere dense and an example of a nowhere dense set which is not totally disconnected. And last question, if you work in R, if A is a closed subset of R, then the two notions coincide. So A is totally disconnected if and only if it's nowhere dense. And since A is closed, meaning saying that A is nowhere dense simply means that the interior of A is empty, okay? Because A equal to A bar in this case. Okay, first question, we know that singletons and Z and Q, so singleton and Z are both nowhere dense and totally disconnected, as we mentioned in the lectures. Okay, so the only connected components of Z are either empty or the singletons. And a singleton actually happens to be both connected and totally disconnected. Okay, so which seems a little bit contradictory, but this is the only extreme case. Okay. Now, Q is totally disconnected, as we observed, because the only connected subsets of Q other than the empty set are the singletons. We proved that. But Q actually is everywhere dense. So the interior of Q bar is just R. It's the interior of R. So Q is totally disconnected, but not nowhere dense. If you consider a circle and just a circle, the boundary, not the disk. If you consider a circle, for example, or just an arc, if you like, it's nowhere dense because it's closed and has empty interior. Okay, contains no ball, but it's not totally disconnected. Okay, it's a connected set having more than one. It's connected. Okay, so and having more than one point. So now, third question, we assume that A is a closed subset of R, and we want to prove that if A is totally disconnected, then the interior of A is empty. So we reason by contradiction. If the interior of A was not empty, then A would contain a non-empty open set by definition, which is a circle, and therefore a non-trivial interval of the form AB open A less than B. But the open interval AB is connected, okay, and not empty, not singleton. Therefore, this is a contradiction. This contradicts the fact that A is totally disconnected. 2 implies 1. So we assume that A has an empty interior, and we want to prove that the only connected, not empty subsets of A are the singletons. So consider a non-empty subset C of A, which is connected. Now, since A is an R, then C is an R. Now, we know that the only connected subsets of R are the intervals of any kind, okay? So including the extreme case, but here we removed. So what does it mean? So if C contains two distinct points A and B, then since C is an interval, the open interval AB is contained in C, actually the closed if you like, and it's contained in A. So if the open interval AB is contained in A, then the open interval AB is contained in a circle, because a circle is the biggest open set contained in A. But the interior of A is empty, then for this is a contradiction. So A cannot contain more than 2 points. Okay, so either 0 point or 1 point. And that's it. So therefore, if we assume that C is not empty, then C is necessarily a singleton, and therefore the only connected subsets, non-empty subsets of A are the singletons. And this, by definition, means that A is totally disconnected. And this concludes the exercises of chapter 4. Thank you for your attention. And in the next video, I'm going to finish chapter 5.